This is Ringing the Changes, a statics analysis of bell crank mechanics. I'm Stephen Wolf.
I'm Xiaomi Salvi.
And I'm John Plakis.
Okay, so what is structural mechanics? Structural mechanics is the science of figuring out how things stand, hold together, resist falling apart under forces like gravity, wind, or weight, or vehicles on a bridge. It is the backbone of everything from skyscrapers to spacecrafts by using math and physics to keep our world steady and to keep everything equal forces. It's what keeps bridges in the sky and stops them from falling, as well as keeping airplanes together and keeping buildings standing. Civil engineers, aerospace, mechanical, and even biomedical engineers utilize structural mechanics.
What is an FBD? A free body diagram is a sketch that primarily shows the forces applied and the direction of the forces, as well as size, dimensions, and angles of bridges, frames, beams, trusses, etc. It is the most important step to analyze a structural component because you can visualize the forces and map out the proper calculations. An example of an FBD is below, where there is a length across the beam, there are reaction forces at AY, AX, and BY, and they are respectively a pin and a roller. There are also forces at C, D, and E along the beam. You could take the moments at A or B to find these forces, or you can take the sum of the forces at X or Y directions. But there will not be an X reaction for C or B because there are, of course, no forces along the X-axis for these forces.
So what is a bell crank? Well, a bell crank is a lever shaped like an L or a belt elbow that pivots at its corner to redirect force or motion through an angle, typically 90 degrees. In the medieval times, like back whenever they had a whole bunch of cathedrals and like with monks and stuff, they used bell cranks in church bell systems, which is a massive bronze bell hanging in a tower that was hooked up to a bell crank and rope. When the rope was pulled, the bell crank pivoted, causing the bell to ring. The bell part stuck due to its historical usage, and crank comes from the Old English word crank, spelled with a C, meaning a bending or twisting tool.
Hi, my name is Sam, and my favorite hobby is snow tubing.
My name is John, and my favorite hobbies are gaming and watching air shows.
I'm Steven, and when I'm not working or doing schoolwork, I like to play video games and board games.
Okay, now we are going to analyze a dual bell crank throttle linkage kit. In the picture shown, we have two 4-barrel carburetors. There are two throttle bars linked to each carburetor. There are two bell cranks, and there is one link connecting these two throttles. And as shown in the free body diagram on the right, we have those two shown, as well as the two bell cranks and the one link. The heights, of course, are going to be marked as well, and the widths between these two bell cranks are going to be equal. So they are marked as W1. The heights as well are going to be the same, so those are going to be H2. And then the bars are going to be, of course, H1 because they are going to be the same length when we connect them to the carburetors. Angles are the same, but AL and AR are different. So we are going to do Pythagorean theorem to find these angles.
Okay, so here is a center pull cantilever bike brake system for bikes. They are a type of rim brake. The force is applied when the handbrakes are pulled, and a cable pulls the center pull cantilever, which has a cable connected to the bell cranks from each side, and when the brake pads then squeeze the rim of the bike, it'll brake. And in my free body diagram, I have these arrows to show all the directions of all the forces being applied.
This is an image of an aileron bell crank. Essentially what an aileron is it's attached to the wing, and whenever the control arm to the flight control system moves, it pivots the bell crank, and the bell crank then pivots again to the control arm connecting to the aileron, and it allows the aileron to move up and down so the plane can change direction. On the right hand side here, I have created a free body diagram of this system here, and a couple of things to note. The typical dimensions are 2:1, so if it's 2 inches wide, it's an inch tall from joint to joint. And then cables are tensioned between 10 to 200 pounds. That's also an important thing to note, and we'll probably be changing those to newtons whenever we go and do our analysis, which is going to be over this system.
All right, for external forces and support forces, what we have above is the aileron bell crank FBD, which was on the previous slide, and we're going to identify the directions of the external and support forces. We assume that AX is going left, AY is going down, FT is going up, SA is going up and to the right. We are going to find the angles of these, and we have found that theta B is 63.43 degrees, theta C is 26.57 degrees. We're going to take the moment about A and say counterclockwise is positive. We're going to do the width multiplied by the height, which is 100 times 200, and we're going to subtract that by 200 multiplied by SA cosine of 50, and we're going to set that equal to 0. And when we solve for SA, it's going to be 155.5724, and we're going to find the reaction forces at SAX and SAY. And when we do that, we're going to do SA, which was found previously, and multiply that by cosine 50 for SAX, and that's going to equal 100. We're also going to do SAY, which is SA multiplied by sine of 50, and that it comes out to be 119.1754. And when we do sum of the forces in the x direction, we're going to do right is positive, which means AX is going to be negative, and we're going to add that by 100, and when we solve for AX, it's going to be positive 100. And we're also going to do the sum of the forces in the y directions, assume up is positive. AY is going to turn out to be negative. We're going to add that by 200 and 119.1754. And when we solve for AY, it's going to come out to be 319.1754.
So after analyzing the external equilibrium, we now move on to trying to figure out the members and the type of stress that they're under, whether it's tension or compression. And to do that, I've chosen to do the method of joints. And so I started with joint A because that was the easiest. And I took the AX value that we got from the previous slide, 100 newtons. So we have 100 newtons going in the left, and I took AY from the previous slide as well, which is 319 newtons going down. And so I just solved for equilibrium at that specific point. So I took the sum of the forces in the x direction, and I found that AC is equal to 100, and it's experiencing tension since all of the arrows are pointing away from the joint itself. It's in tension. And then the sum of the forces in the y direction, same thing. I got AB equals 319 newtons in tension. So then moving on to joint B, this one was a little bit more trickier. I had to find the angle of that specific point at point B in joint B. I had to find the angle that theta B was, which is also explained in the previous slide, and actually we solved for SA and SAY in the previous slide, and I just carried those values over here. So for here, I had used SAX is 100 newtons going to the right, SAY is a 319 newtons going up. And then we also have 319 newtons going down from AB. We took AB and we put it here, and it's going down because it's in tension. So whenever you switch spots, it's not changing. It's always going to be in tension. And then we have our BC. We found our BC. We have cosine of 63.43, and we found that in the previous slide as well, showcasing that tangent of -1 is 200 over 100. And that's what I kind of got here. So then the sum of the forces in the x direction equals 100 from the AX minus the BC cosine of 63.43. And I found that BC is experiencing 223.6 newtons of compression on joint B. So there we go. So from the previous two slides, all of it has really led up to this particular image. And here we just show all of the members, whether they're in tension or compression, and then all of the forces that are acting on this particular belt crank. So we've had fun trying to figure all this out. All right, thank you very much. Science can amuse and fascinate us all, but it is engineering that changes the world. Science fascinates us with principles like force and balance, but engineering uses free body diagrams to isolate systems and applies equilibrium equations to design real-world solutions. It's the practical application that transforms scientific wonder into tangible change. Look at this tug of war with a belt crank caught in the middle. The teams are pulling hard, showing the chaotic forces at play. Free body diagrams are fun because they let us play referee. Without FBDs, the forces would win and our planes wouldn't fly safely.
A big thanks to Professor Wise, my crew, and Caffeine. You really cranked this one home. And for references, we did Dual Bell Crank Throttle Linkage Kit by Quartermax Racing, Understanding Bicycle Braking Systems by Iflific, Aileron Movement for a Model Plane by Airport Cat on YouTube, Airplane Cable Tensions and Control Surface Rigging by Jay Ship over Cessna Owner Organization, Cable Tensiometer from Aircraft Tool Supply on aircrafttool.com, and KR Super 2 on krsuper2.com.